Semi-supervised training has become a popular way to increase ASR performance when transcribed speech data is limited. If we train a seed system on what supervised data we do have, we can then decode any additional non-transcribed speech data accessible and use the resulting predicted transcripts as pseudo-labels to train a larger downstream model. But central to this training regime is a conundrum. How exactly does semi-supervised training lead to gains when we're relying on pseudo-labels? This implies the seed model's predictions cannot be poor, for this would result in error propagation, but we want this training regime to work when the seed is not trained on much data. But some naive confidence filtering of pseudo-labels would not then allow the downstream model to learn anything new. It is this conundrum that we now dissect, beginning with the following intuition. It is true that the seed acoustic model, if relying on learnt frame level information alone, will have not seen enough labeled data to be confident about all its phoneme decision boundaries. But what happens when we add reliable utterance level information to this example? We believe this is the key to successful ASR semi-supervised training, that external and reliable sequence level information can be fed to the system to supplement, guide, and reduce uncertainty of the seed acoustic model's initial frame level prediction. And where does this sequence level information come from? Well, from the language model, externally trained, but still constituting part of the initial seed system. And thus, when considering acoustic and language model independently, and specifically considering the language model's guiding role, we reach the following hypothesis. Optimally performed semi-supervised training may in fact be much more sensitive to quality of language model than the acoustic model or seed system overall. On Tagalog, we conduct experiments to assess this. By constructing a hybrid model-based pipeline, we can isolate acoustic and language model components and independently switch out these components for artificially weakened variants trained on less data, whilst holding the other constant. We can then chart how using any particular acoustic language model combination affects the gains that can be made via semi-supervised training by plotting the initial word error rate of the seed against that achieved after pseudo-labeling and retraining occurs. For example, what happens when we use our highest quality language model but progressively weaker acoustic models? Well, noting that if a point lies below y equals x, this indicates gains, we can clearly see that gains are made across the board from semi-supervised training, even when the initial system's word error rate was high. Though these systems' frame level predictions will be worsening, it does seem that good quality language model information can be relied upon. But is this true when we do the opposite? Utilize a good acoustic model, but swap out the language model for successfully weaker variants? No. Here we see a very different trend, and thus this constitutes just one of the pieces of evidence we find for our hypothesis. For further details of our setup, motivation, and discussion of the rest of our experiments through this novel lens, see our paper.